Welcome to the viewers for the lecture number 132 in strength of materials. In the last lecture, lecture number 131, we have discussed the types of beams, different types of loads, bending moment, shear force, and some basic calculation procedure. Basic calculation procedure I am discussing elaborately because this will be required in many occasions when you deal with different types of structures. So this basic will have to be very strong. And now in this lecture, we will take up two cases of simply supported beams. One beam with a point load and UDL, another beam with a uniformly varying load. I'll be discussing more than one procedure because I'm not particular about solving a particular problem. That will be simple, but with a long-term vision, I'm just giving detailed calculations, sometimes more than one calculation, of which you can skip one calculation, etc. So my aim is to discuss the general procedure. So this introduction, once again I'll tell you that this is lecture number 132. We are going to discuss bending moment and shear force for simply supported beams in this lecture. In problem number 1, this is given in the form of a figure. Sometimes they will give only in the form of a text. I'll read the same problem in the form of a text. A simply supported beam of span 10 meters is subjected to two point loads of 40 kilonewtons and 50 kilonewtons respectively respectively at 2 meters and 4 meters from the left support, and an UDL of 3 kilonewton meter and of 4 meters length over the near the right support. Calculate the bending moment and shear force at a section X, and also calculate the bending moment and shear force and draw the bending moment diagram and shear force diagram. Right. This is the problem. You can see the problem. Note down the loads, including the UDL, etc. Right. Now, so these are the actions, external loads. Now, the support A and the support B will have to offer the reaction. The loading is not symmetrical. Therefore, we have to find out what is the value of RA, what is the value of RB. For finding out the value of RA and RB, for example, to find out the value of RA, we have to take moment about the right support B. Moment about right support B. Right. Right. Taking moments about B. We see there is a reaction at the left end, RA into 10 meters. We have to refer all the distances to we are taking moment about B, we have to refer all distances to the point B. So normally used advice, after some stage in a tension, we will forget what is the point to which you have to take moment. So better when you take moments about B at the point B, you have some pencil or some object so that you will refer all the distances to the point B. Right. So RA into 10 minus UDL 3 into 4. 3 kilonewton per meter over a length of 4 meters. So 3 into 4 total load. The total load will be acting at the centroid of the center of gravity of UDL. That is 4 meters by 2. So 2 meters from B or 8 meters from A. So that is the point where the total load 3 into 4, 12 kilonewtons will be acting. So 3 into 4, we are taking moment about the point B, therefore into 4 by 2 minus this 50 into 6 meters up to the point B minus 40 into 8 meters up to the point B. So that's about these terms. So calculating RA will be equal to 64.4 kilonewton meter. RB equal to total load minus RA. Total load 40 plus 50 plus 3 into 4, 12. Total load is 90 plus 12, 102 kilonewtons. 102 kilonewtons. So total load is 40 plus 50 plus 3 into 4 minus RA. Support A offers a reaction of 64.4 for the given load position. So RB equal to 37.6 kilonewton. As I told, this calculation will be correct if your RA is correct. So second part of the calculation will not be necessary. However, for checking, I just given the alternate procedure also. Alternate procedure is not a must if your value of RA is correct. Right. Now what I am doing is taking moments about A, the support A. So from here, RB into 10 meters minus 40 into 2 meters minus 50 into 4 meters minus 3 into 4 into 8 meters up to the point A. To the point A. So 8 meters. That is what is this. RB into 10 minus 40 into 2 minus 50 into 4 minus 3 into 4 is the total load. From A, it will be acting at a distance of 6 plus 4 by 2 equal to this value. So that gives RB equal to 37.6 kilonewton. So this is 37.6 and here also it is 37.6. Right. So that is about finding out the reactions. Next is finding out the shear force and bending moment at a given section. You have been asked to find out the bending moment at a given section X. X is 3 meters from the left hand support. For convenience, we just divide the beam into 2. So actually, when you do the problem, these drawings are not necessary. They only to make you to understand the concept clearly. Right? Right. You have divided the beam into 2. Right. The shear force at the section equal to, we know shear force is the algebraic sum of the vertical forces considered to the left of the section or to the right of the section. I am showing both calculations, but any one calculation will be sufficient. Right. Coming to the part AX, you got one reaction, one load. So algebraic sum of vertical force, one is upward, the other one is downwards. So 64.4 minus 40 equal to 24.4 kilonewton is the shear force. It is left up. Left up is positive. Right, left up is positive. So 24.4. Same thing. This is extra calculation. Considering the portion to the right of X. Right of X. RB is 37.6. Already we know. Or 37.6 minus, there is a downward load 50, there is another downward load 3 kilonewton per meter of 4 meters length 12. So 37.6 minus 50 minus 3 into 4 equal to minus 24.4. Same value 24. Whether you consider the left of the section, right of the section, the value will be the same. So on the left, you have the value upwards. On the right, you have, considering the right hand side portion, the value is negative. We know, as far as the sign convention is concerned, left up, right down is positive. So here it is left up, so it is positive. Here, the net force is minus, downwards. So this is the shear force here is to the right of the section. To the right of the section, the shear force is positive only. Here also it is positive only. Sign is negative. Left up, right down is positive. When we plot the shear force diagram, at the section X, the shear force will be positive. Left up is positive, right down is positive. Or you can say clockwise is positive. Clockwise is positive. This is clockwise is positive. Right. That is about the sign convention. So that means if it is left down, it is negative. Right up is negative. So, and here one more point. So we have got the shear force of 24.4 kilonewton, considering the loads only to the left of the section or only to the right of the section. At the section X, actually, when you add the two values, the algebraic sum will be equal to 0. We know the condition sigma V equals 0, algebraic sum of all the forces in the vertical direction, considering left hand side, right hand side, etc., equal to 0. That is the equation of, that is one of the equations of equilibrium. Sigma V equal to 0. That is why we take the forces either to the left only or to the right only, because when we are going to define, of course we already defined what is shear force. It is the algebraic sum of vertical forces considered on any one side, either to the left of the section only or to the right of the section only. If we add everything, algebraic sum will be 0. When you consider both left hand side and right hand side, the value will become 0. Right. Now coming to bending moment, same section X, bending moment. Now RA into 3 meters. For the section X, it is 3 meters. RA into, because we know moment equal to force into the perpendicular distance. Now this is RA into 3 meters. You have another force, algebraic sum of the moments, right? RA into 3 meters minus 40 into 1 meter is the bending moment. Because we are finding out the bending moment at the section X, you have to refer all distances to the point X. RA into 3 minus 40 into 1 is the bending moment at the section. This value equal to 153.2 kilonewton meter. Or, again, it is extra calculation. We can take the moment at the section from the right hand side also. That is RB into 7 meters. RB into 7 meters. That is anti-clockwise. Minus 50 into 1. 50 into 1 up to the point X. Minus 3 into 4. This will be acting at the center of gravity, namely 2 meters from the right support. Actually, this is total 7 meters. So 7 minus 2 equal to 5 up to the, from the center of gravity of the load up to the point at which the moment is required, the distance is 5 meters. So minus 3 into 4 into 5. That is what is the calculation. 37.6 into 7 minus 50 into 1 minus 3 into 4 into 7 is equal to 153.2. Right. So moment is left clockwise positive, right anti-clockwise positive moment as far as bending moment is concerned. So this is a section. To the left of the section, if the moment is clockwise, it is positive. To the right of the section, if the moment is anti-clockwise, it is positive. So left clockwise is positive, right anti-clockwise is positive. This moment will be called sagging moment. Sagging moment, which will cause tension at the bottom. This is when this 153.2, 153.2 will be clear when we draw the bending moment diagram, right? So that is about finding out the shear force at a section and the bending moment at a section. Now we are interested in getting the bending moment diagram and shear force diagram for the total beam, for which we have to find out the shear force at C, shear force at D, shear force at E, and the variation, etc. Similarly, for drawing the bending moment diagram, you have to find out the bending moment at A, bending moment at C, bending moment at E, and bending moment anywhere in between, and also the variation. These things you'll have to find out step by step. So first let us find out the shear force. Coming to shear force at C equal to, shear force at C means, just to the right of C, just to the right of C. That is algebraic sum of the vertical forces. That is RA minus 40. That's all. Shear force at D means it is RA minus 40 minus 50. That's the calculation here. See, here RA 64.4. Shear force at A equal to RA itself 64.4. Shear force at C equal to RA minus 40 24.4. 24.4 just to the right of C. FD means RA minus 40 minus 50 is equal to minus 25.6 kilonewton. Sum of the vertical forces. Algebraic sum of the vertical force. Total upward force minus total downward force. Then FD equal to same minus 25.6, because between D and E there is no external loading. Therefore, there will be no change in the shear force. It will be, so the shear force just to the right of D will be the shear force at the point E also. Then the shear force in the portion EB. What you can do is, now here there will be linear variation. So how to assume the linear variation? So consider a section X4, X4. Consider the load only to the right. From the left also it can be taken as you told earlier. The number of terms will be more. When you consider the loading on the right hand side, the number of terms becomes less. Right. So both will give the same value. Right. Considering the load to from the right. Measuring the distance x from the right hand support, the shear force at the section X4 equal to, it is simply the sum of the vertical forces. At some section distance x from A, x from B, it is 37.6 minus the loading. Loading is 3 kilonewton per meter. You are considering a length of x. Now we are calculating the shear force. Shear force means left up, right down is positive. Here the shear force is, the reaction is in the upward direction. So right up is negative. So minus 37.6, equation is minus 37.6 plus 3 into x. That is, this load is right down. Right down is positive, right up is negative. So minus 37.6 plus 3 into x meters to the right of x4. So this is the equation, right? So right up is negative and this is the value. When x equal to 0, it is minus 30. When x equal to 0, substitute 0, it will be minus 37.6 only. If and at the point E, here, since is x is measured from the right support, x equal to 4 meters to the point E. So Fe equal to minus 37.6 plus 3 into 4 is the value of x. So it is minus 25.6. The main point is, this is the general equation for the shear force. Minus 37.6 plus 3 into x. So that means it varies. The variable is x. The power of x is 1. Therefore, the variation will be linear. This is very important. Linear. So this is the shear force diagram. 64.4. Just to the right of the point C, it is 24.4. Up to the point D, there is no load. Again, it is minus 25.6. Up to the point E, there is no variation, 25.6. And here you have linear variation. It is minus 37.6. And RB is minus 37.6. You will be starting from this point. This is RA. This is the variation of shear force which you have calculated. And here you have to plot the value of RB in the upward direction. That will complete the shear force diagram. Right. Now again, this is extra calculation, not necessary. This is only to develop confidence. For example, if we take section X1, here, X1, you have to the left of X, we have only RA. So the shear force at X1 is equal to RA only. No X, no X power 2, nothing. That indicates from A to C till we meet the next load, the shear force diagram is constant. Similarly, When we take section x2, the shear force x2 equal to RA 64.4 minus 40 minus 50. It's only algebraic sum of the vertical forces. No x term. Therefore, that is also constant. Only here you will have the variation that we have just now we have discussed. So this is to show that they are independent of x, therefore they are constants. In the portion EB already we have discussed. The general equation is say minus 37.6 plus 3x. X is the variable. So substituting x equal to 0 and x equal to 4 meters, you get the value. The main point is the variation of shear force is linear. Right. Similarly, coming to bending moment already we have calculated. No, only for the section X we have calculated. Now general calculations only now we are going to do. That is, we will discuss here. Bending moment at C equal to bending moment at A is 0, simply supported end. And bending moment at C equal to, consider the force to the left. To the left, there is only one reaction, 64.4. The vertical force into horizontal distance. It is force into the perpendicular distance. 64.4 into 2 is the bending moment at the point C. At the point D, it is 64.4 into 4 minus 40 into 2. So this is clockwise, this is anti-clockwise. Left clockwise positive, anti-clockwise negative. So it is 64.4 into 4 minus 40 into 2 will be the bending moment at the point D. Coming to the calculations, MA equal to 0, MC equal to RA into 2, 128.8, MD equal to RA into 4 minus 40 into 2, 177.6, and ME, the moment at the point E here is RA into 6 meters. ME means you would refer all the distances up to the point E. RA into 6 meters minus 40 into 4 meters minus 50 into 2 meters up to the point E. So that will give the bending moment ME equal to this value, RA into 6 minus 40 into 4 minus 50 into 2 equal to 126.6 kilonewton meter. Right. Now the bending moment at E can also be obtained by considering the load to the right of the section. To the right of the section, we have one reaction and one point load. UDL. So ME equal to RB into 4 meters up to the point E minus 3 into 4. Total load is 12 kilonewton. The 12 kilonewton will be acting at the center, namely 2 meters from the point E. So that is how ME equal to RB into 4 minus 3 into 4 into 4 by 2. That is equal to 126. So whether you consider the loads to the left of the section E or to the right of the section E, the value will be the same. Right. And this is the bending moment diagram. So these are ordinates we have calculated already. 122.8, namely 128.8, then 177.6, 126.4. These values are plotted here. So here bending moment diagram will be linear, and second degree. Now we have directly calculated. This calculation will be sufficient if you are familiar with the calculation. After doing 1 or 2 problems, this will be sufficient. But how it is linear variation? You will have the doubt now. So this is the alternative calculation. This need not be done. Only for explaining the procedure. Right. Now here section x1, RA into x. RA measuring x from the left, RA into x. RA into X equal to 64.4 into X. So the equation is in terms of X. Power of X is 1. Therefore, you will have linear variation. Only to prove that we have done the calculation here. Similarly, X2 will also be 60. Again, all values are measured from X. I mean the left support. For section X2 also, it is RA into X minus this load into this distance. The distance is X minus 2 meters. This is already known. Total distance is X. So this is X minus 2 meters. The aim is to prove that it is also linear variation. That will also be second X2 equal to RA into X minus 40 into X minus 2. Right. So this is also in terms of X. In terms of X. So again, it shows that the variation of bending moment is linear. Substitute X equal to 2 meters and X equal to 4 meters, you can get the value of MC and MT, because that is the equation for the portion between C and D. X2 is in CD. Right. Now coming to the third one also, you can prove in the same line. On the same line, you can take bending moment X3 also, that will also be in terms of X. Right. Now for the portion BE, you can consider all the forces from the left, but the number of terms will be more. So to simplify our calculation, we consider the forces to the right of the section. Right. Now when you consider the portion to the right, the bending moment at XX equal to 37.6 into X. X is measured from the right hand support. 37.6 into X minus 3 kilonewton per meter. We are considering this section. This length is only X. So 3 into X will be the load. The 3 into X will be acting at X by 2. We are considering only this portion, XB only. 3 into X into X by 2 up to the point, up to the section XX, because we are taking moment about the section XX. You have to refer all the distances to the section XX. So 37.6 into X minus 3 into X by 2. Here again, the aim is to show that it is a quadratic equation. So second degree variation. Only for that this calculation is shown. Now the viewers can easily understand the meaning of this equation. RB into X minus 3 into X by 2. So the 3x square by 2. So substitute X equal to 0 meters, you will get the bending moment at B. Substitute X equal to 4 meters, you will be getting the value of bending moment at E. You will find that ME, considering the loads to the left of the section as well as considering the load to the right of the section, ME will be the same. So this is about, this is only to prove that the linear and the quadratic variation, but every problem for every loading, you cannot do this calculation. Because after doing one or two problems, you yourself will come to a conclusion that if it is a point load, the shear force diagram will be constant, bending moment diagram will be linear. If it is uniformly distributed load, the shear force diagram will be linear, the bending moment diagram will be quadratic or second degree variation. We are going to discuss one more load, uniformly varying load. So the variation will be second degree, the shear force diagram will be having second degree variation, and the bending moment diagram will be having cubic variation or third degree variation. If this is clear, then you can straight away do the calculations without considering this X, etc. You can just ignore this alternate the specimen calculation or alternate calculation can be skipped once this become there. But this equation will be useful for whatever problem we do. How to deal with point load, how to deal with uniformly distributed load, how to deal with uniformly varying load, how we get the equation, why it is quadratic, why it is cubic, all these things will be clear. You will be confident. Right? Now that's about the bending moment diagram and also the alternate calculations for bending moment. So this is a sign convention already we have discussed. If this is the beam, overhanging beam, both sides overhang. Left clockwise is positive, right anti-clockwise is positive in the simply supported portion. This will be subjected to sagging moment. Sagging moment. Tension will occur at the bottom. For the overhanging part, it's a cantilever. Cantilever. Not exactly cantilever. Only it will be a cantilever only when this is fixed here. However, it is overhang. And here you will have negative. This moment will be negative. The overhanging portion, a hugging moment. Tension will be at the top, and the behavior of the beam is shown. Now here, right. On the left hand side also, in the overhanging part, it is negative. So left clockwise positive, left anti-clockwise negative. Right clockwise, right anti-clockwise positive, right clockwise negative. So when we do a few problems, this will become very thorough. This is about the sign convention. Sign convention for shear force and the sign convention for bending moment will have to be thorough. One will have to become very strong because in certain books the opposite sign convention will be followed. When the opposite sign convention is followed, it need not be under confusion. The individual will have to become strong in the basics, right? We will take the next problem. Next problem is that of a simply supported beam subjected to uniformly varying load. Previously we discussed UDL and the point load. Now UVL, uniformly varying load. So here the span of the beam is 6 meters. Span of the beam is 6 meters, subjected to a uniformly varying load, varying from 0 at the left support to 30 kilonewton per meter at the right support. Uniformly varying load. Sometimes a trapezium will also be given, varying from 20 kilonewton meter at the left end to 40 kilonewton meter at the right end. There we have to consider the load as two parts, one rectangle and one triangle, or two triangles. So like that you have to take, right? Now here uniformly varying load. Now taking moment about B for finding out the reaction. This is the action. To find out the reaction RA and RB, take moment about B. Taking moment about B, RA into 6 meters is the moment due to RA at the point B. Coming to this load is uniformly varying load. So the total load will be half into 6 into 30. 6 into 30 is the ordinate. Half into 6 into 30 is the total load. Area of the triangle. The total load will be acting at its centroid. That is 1/3 of the distance from this end, namely 1/3 of 6 equal to 2 meters, or 2/3 of 6 meters from the left end. That depends upon whether we are taking moment about the point A or about the point B. Now we are taking moment about the point B. Therefore, the total load is half into 6 into 30 equal to 90 into, from here it is 1/3 of 6 meters. We are taking moment about the point B. So equal to, this is the equation, equal to 0. MB equal to 0. Right. So this is only for illustration, right? RA equal to 30 kilonewton. RB equal to total load minus RA. Total load is half into 6 into 30, namely 90 minus 30 equal to 60 kilonewton. So that's about the reactions RA and RB. Right. Now, to get the shear force diagram, bending moment diagram, you consider a section XX at a distance X from the left hand support. Now, this ordinate of the loading diagram at the section X equal to, for 6 meters, this value is 30. For X meters, what is the value? For 6 meters, it is 30. For X meters, what is the value? That is equal to 5x. X is unknown. X is the variable, right? phi x. Right. Now, when you want to find out the shear force at the section XX, you have to consider the loads to the right of the section or the left of the section. Now, considering the forces to the left of the section, the shear force at the section X is equal to RA minus this load. Algebraic sum of the vertical forces. RA is 30. This downward force equal to half into X into this ordinate. Ordinate is phi x. Half into X into phi x. That is the so the equation is 30, namely RA minus half into X into phi x. Therefore, that is 30 minus phi x square by 2. We are calculating the shear force. The general equation for the shear force is of second degree, x square. Therefore, the shear force diagram will have a second degree variation. Right. Now, in this equation, substituting x equal to 0, we will get the value of shear force at the point A. Fa equal to 30 kilonewton. Substituting x equal to 6 meters, the shear force equal to 30 minus 5 by 2 into 6 square. 5 by 2 6 square equal to minus 60. So, it varies from plus 30 to minus 60. Somewhere it will change the sign from positive to negative. Right. Now, the variation is second degree. Right. Now, to find out the location where the shear force changes sign, what we do is, where it changes sign, the shear force is 0. Changes from positive to negative, or at the section, shear force is 0. So, shear force at x equal to 30 minus 5x square by 2 equal to 0. That will give you the value of x at the section where the shear force changes sign. SF equal to 30 minus 5x square by 2, the value is 0. So, on solving this, you get the value of x, which is equal to 3.462 meters. So, at 3.462 meters from the left hand support, you have to show the change in the sign of the shear force diagram. This is the shear force diagram. As we have discussed earlier, it is second degree. The equation is 30 minus 5 square by 2. The positive shear force of the left support is 30. The shear force of the right support is minus 60. So what we have to do is, for drawing the shear force diagram, we have to start from this line. We know shear force of the left support is 30. So mark it upwards. And at 3.462 meters, the shear force changes sign. It becomes negative. It is minus 60. We will be stopping here. Then we have to mark the value of RB to close at the point, the horizontal line, close at the horizontal line. That is how we have to mark RA, then the variation. So this variation also can be calculated every 1 meter interval. That is not necessary. If you know the variation and if you know where it changes sign, that is enough. So that is the shear force diagram, which is of second degree variation. Right. Next is that of bending moment. Again, the same figure, this figure. We are considering this figure. This same figure. Now here, we find out the bending moment at some section X. Bending moment at same section XX. Bending moment equal to RA into X. RA into X is this value minus, you know what is the meaning of this phi x? Half into x into phi x. Half into x into phi x is phi x square by 2. Phi x square by 2 is the total load. Area of the triangle will give you only the total load. The total load will be acting at the centroid. We have considered a triangle of length x. Therefore, at a distance x by 3 from this end or 2x by 3 from this end, the total load will be acting. We are taking moment about the section x. Therefore, we want the value of x by 3. Therefore, the moment equal to RA into x minus the total load into x by 3. So this on simplification gives the equation A. Equation A is 30x minus 5 by 6 into x cube. So this indicates that the bending moment diagram will be having a cubic variation, third degree variation. In this equation, when x equal to 0, so this is 0, therefore the bending moment is 0. Left support. Right support, x is 6 meters, 30 into 6 minus 5 by 6 into 6 cube, that is also 0. Right support is simply supported. Left support A is simply supported, bending moment is 0. Right support is also simply supported, bending moment is 0. Then how to plot the bending moment diagram? You have to find out the maximum bending moment. For finding out the maximum bending moment, one way is the maximum bending moment occurs where the shear force changes sign. Where the shear force changes sign, bending moment is maximum. We know that the shear force changes sign from positive to negative at 3.462 meters from the left support A. So substituting the value of x in the equation, for mx, equation for mx is 30x minus 5 by 6 x cube. So 30 into 3.462 minus 5 by 6 into 3.462 cube will give you the numerical value of the maximum bending moment, mmax. That has to be marked in the bending moment diagram. Here I have not calculated. Mmax will have to be calculated and written here. In this equation, substitute x equal to 3.462 and you will get the numerical value. That value will have to be marked at a distance of 3.462. So this gives the location of maximum bending moment and this gives the value of maximum bending moment. This is the bending moment diagram having a cubic variation. One more point before concluding. The value of x we have simply taken where it changes sign. The alternate way of calculating, I told you alternate way is not needed. Either do this or this. Only for making the viewers clear, I am just giving both procedures. Any one will be sufficient. If you calculate the value without any error, that is enough. Right. This is the alternate way. Again, as I told earlier, these calculations will be required in number of places throughout your career. That is why just I'm concentrating on all these things, right? So x can also be obtained using the equation dmx by dx equal to 0. That is d by dx of, at the point of maximum bending moment, dmx by dx will be equal to 0. Or d by dx of, this is the equation A, 30x minus 5 by 6 into x cube equal to 0. This on differentiation with respect to x will give you this equation, and this equation has to be equated to 0. So that will also give you x equal to 3.462, giving you the location where the bending moment is maximum. So by any of the procedure we can follow, we can find out the location of maximum bending moment and also the maximum bending moment. So that completes two problems dealing with three different types of loadings: point load, UDL and UBL. And that completes this lecture. I thank all the viewers for the patient listening. Thank you. Thank you.